In this presentation, I'll talk about some algorithms that computers use to quickly find data, as well as some ways they sort data. Each year, the telephone company produces two phone books, one with phone numbers for residential houses and one with phone numbers for businesses. If they got lazy and just printed phone numbers in the order which they were connected to the service, it would be easy to maintain, and it could be useful if you wanted to find a new or long-running business. But let's say you wanted to buy some fertilizer for your garden, and you wanted to find a landscaping supply shop. You could pick a random page and keep looking until you found one, but you might end up covering the same page more than once. You could start from one end and then work your way to the other, and stop if you found one that was close enough. But to be sure that you found all possible businesses in case you wanted to call around and get a good deal, you'd have to look through the entire book. This would take a long time, and people probably wouldn't do it. This is why sorting is good. If the book was sorted into alphabetical order, you could open the page anywhere and see what's on the page. If the letter was before L, open a page further into the book, and if it was after, you'd open a page before it. You would then repeat this until you were at the section where landscaping could be. You could also use an index to see what sections of the book has, and there might be some listed under gardening. But let's ignore the index for now. This search is called a binary search because when you look at a page you're at and then you go one way or another, you're at an ordered list, and you then cut out half of the remaining area to be searched each time that you do a decision and go left or right, go forward or backwards into the book. If I had a deck of cards numbered from 1 to 100 and dealt 16 of them face down at the table, and I told you they were sorted, so the biggest card was to your right and the smallest card was to your left. If you wanted to see if 27 was one of the cards, you'd start in the middle and turn over the card to see what it was. One of the three things would happen when you turn over the card. If the number on it was less than 27, and you could pick a card to the right of it, the number is more than 27, and you pick a card to the left of it, the only other possibility is that the number on the card is 27, and you stop searching. Of course, you chose the card in the middle. If the card wasn't 27, you no longer have to look at half of the cards. Now, if you turned over 26 or 28, you might decide to turn over the card to the left or right of the one you've just turned over. Of course, they're sorted, and then 27 has to be next to it if it's there. But to consistently find the answer to the quickest, or as a general purpose algorithm, we would choose the middle card of the remaining unknown values and turn it over. Each time we reduce the number of items we need to look by half, and this comes in useful when searching data with hundreds of thousands of records. The problem could be representative of a computer program implementing student database, and each student has a unique ID number. Depending on how the software is implemented, the card may have other information on it like the first name and surname and contact details, or it might contain a pointer to another memory address where this information is, but that level of detail is beyond today's talk. So going back to the 100 numbered cards, we want a way to quickly and efficiently sort them, so subsequent searching is easier. So now, imagine some cards are on the table in front of you, but all of the cards are now showing their numbers, and they don't need turning over. We need to arrange them so that the smallest card is on the left, and the largest card is on the right. One way we could do that is by shuffling the cards and then seeing if they're in the correct order. But this would be a terrible way to do this. If we were wrong, then we would shuffle them all again and check them all again. We need to do this methodically, and one way to do it is to start at the left and work our way to the right. If we check the value of the current card and compare it to the value of the next card, we can swap the cards if one of the left is greater than the one on the right. We keep doing this as we work our way all the way along to the end, swapping every time the left card is less than the card on the right, and by the time we get to the end, we know that the largest card is now on the right-hand side. We can then repeat this and start from left to right, again, swapping each time, until we then find the second highest. And then this can be repeated until only two cards need to be checked, and they're the two on the very left. Once that is done, the list will be sorted. This is known as the bubble sort, But that contains a lot of checking and swapping, all of which takes time to do. An improvement to this is to remember the value of the largest card, where it is in the list, and then work from there through the list and move the biggest card to the right-hand side. Each time we go through the list, we select the biggest card and move it to the end of the unsorted area of the list. This would mean that we could start with the first card on the left, and because it's the biggest, the only one we've seen so far, it's now considered the biggest of everything. When we work through to the right hand, we update the information on which is the biggest one we've found so far as we go. And once we reach the end, we then swap that card at the end with the card we've identified as the biggest. This process is repeated again and again, each time shrinking the unsorted area of the list, but there's still a slightly better way. And the algorithm just described is known as the selection sort because each time we pass through, we select the biggest card. Each time we search through the unsorted list, we have to search through all of it. If we move the cards up and put them into a sorted area, it'll speed up where they have to be placed. The insertion sort gets its name because the numbers are inserted into a sorted area of the list. In this, we start with a single element, declaring it sorted, and then take the remaining unsorted elements and insert them into the correct spot of the sorted portion. Each time we add it, the sorted portion grows. While we've had a look at sorting and unsorted numbers, it's also worth considering effort it takes to sort a nearly sorted list of numbers. Let's say you have 20 cards face down on the table, which are sorted, and 5 more are drawn out and put on the right-hand end. If you use bubble sort, you would have to bubble all 25 cards as before. And the same with the selection sort, all 25 would be done. But an insertion sort that's coded with some optimizations, like first checking if the number could go on either end of the already sorted list, can reduce the total time required to sort a list that's minimized. If we would declare that the first card sorted, and then check the next one, checking if it's greater than the one before, and if it's so, go straight to expanding the sorted area, and then go check on the next card. This would mean it would quickly move through the first 20 cards, as they're already sorted in place, and the last 5 might result in moving and shuffling the majority of the list. There are a lot of other sorts available for programmers, and this presentation is just scratching the surface. If you'd like to hear more of this type of presentation, please hit the like button. If you have any requests for subjects for me to talk on, please leave a comment and I'll see what I can do. Thank you for listening. I hope it's been helpful.